Hey everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. Today we're going to talk about Henry's Law, and this is quite a short lecture because there's not that much to say about Henry's Law because we've already covered kind of the important stuff. All the sort of theory we've already covered because we've already talked about the partitioning between the pure phase and I'm trying to get my pen to work here. Hold on a second. Pen. Between the pure phase and the air. There we go. We talked about the partitioning between the pure phase and the air, and we talked about the partitioning between the pure phase and the water, right? So we've already talked about all that, and now we're just going to complete the triangle here and talk about the partitioning between air and water. So we've already covered a lot of the theoretical stuff about salinity and co-solvents and vapor pressure and all that stuff. So this is going to be a relatively short lecture. So we have again this figure from the original, first edition of the textbook, which showed you the ranges of Henry's Law constants that you might expect here for the same classes of organic compounds that are typically, of importance to us as environmental organic chemists. And what I want to point out is that, we're going from about 10 to the 4 to 10 to the minus 4. And that's actually a fairly short range. If you compare that with, I'm going to skip forward here, to vapor pressure. Vapor pressure ranged over 12 orders of magnitude here, and the solubility was also ranging over about 12 orders of magnitude. But the Henry's Law constant is a much shorter range, only about 8 orders of magnitude. And one of the questions is, well, why? And we'll talk about why. Okay, so we have, first I have to do this math. I hate the math, you hate the math. We'll just get through it quickly, okay? Trust me. It sucks. So the fugacity of our compound we've said that by sort of definition, we're going to call it equal to the partial pressure of the compound under those conditions, which is equal to its activity coefficient times its mole fraction concentration times its ideal partial pressure. Okay, and of course, if we're in an ideal solution, then the activity coefficient would be equal to 1. So we have the partial pressure here and the mole fraction concentration, and so that's where we get our equilibrium partitioning between gas and water. So if the activity coefficient is constant, then we can say that the fugacity of our compound I in the liquid is equal to its partial pressure, which again is equal to the same thing, and so we can call this activity coefficient times partial pressure here, we can call that the Henry's Law constant. Because remember, the activity coefficient in the liquid is equivalent to 1 over Csat. Okay, so we'd have vapor pressure divided by Csat here, and that would be our Henry's Law constant. Okay, so another way of arranging that is that it's the actual vapor pressure. This is the theoretical. This is the actual vapor pressure now, because we're getting that from over here. We're just rearranging this equation. We're moving the mole fraction concentration over here under the vapor pressure. So the Henry's Law constant is the vapor pressure of the chemical divided by its mole fraction concentration at equilibrium with each other. Okay, and again, we could call that equal to the activity coefficient times the theoretical partial pressure, like the saturation partial pressure, but no one ever uses this. We hate activity coefficients, so we just do everything we can to avoid them. And we also hate mole fraction concentrations. Those are stupid, which is why we have the little apostrophe here. To get rid of the apostrophe, instead of doing mole fraction here, we just do molar concentration right here, which is what everybody wants to use. And so this is our true sort of Henry's Law constant, which is the partial pressure of the compound in the gas phase divided by its concentration in the aqueous phase at equilibrium. Okay, so we've gotten rid of our little apostrophe, but if you think about it, this pressure has units of something like pascals or atmospheres or millimeters of mercury or bar, whatever pressure units you want to use. And then the concentration down here has got units of something like mole per liter or mole per cubic meter. So when you divide one by the other, you get some strange units for Henry's Law. Henry's Law's got these weird units of something like Pascal meter cube per mole or Pascal liter per mole. But in many cases, it would be a lot more useful to, instead of having partial pressure up here, let's just express it as a concentration. Just like we do for water, we have like moles per liter of water. Why can't we have moles per liter of air? And then moles per liter divided moles per liter would get rid of the units, essentially. They'd be dimensionless. Okay, so that's not truly dimensionless because you have moles per liter of water divided by moles per liter of air. Yeah, the moles cancel, but you still have liters of water and liters of air, which are not quite the same thing. But we still call this dimensionless, even though it's maybe not totally dimensionless. And in the parlance of your book, they're using capital K, little a, in this case little l for whatever the solvent is. In your book, they like to talk about air to other solvent partitioning, not just air to water, but air to all kinds of solvents. But I find that pretty confusing. So we're just really going to focus on the air to water. So the dimensionless Henry's law constant will be written as KAW. Okay, when you see KAW, it means dimensionless units. When you see KH, it means pressure units, like these units. Okay? So just try to keep your units straight. That's the hardest thing about all of Henry's law, is just keeping the stupid units straight. So as you can see from this equation right here, basically this part of it is saying that the Henry's law constant is equivalent to the vapor pressure divided by the solubility, right? Because this is the vapor pressure, and this is, the activity coefficient, which is 1 over CSAT. So you can estimate the Henry's law constant as being roughly equivalent to vapor pressure divided by solubility. And this is a thing that they used in the first edition of the textbook. It's a concept that they introduced. Now, it's not always true, because this is true. It is true, but it's true at saturation. And of course, in the real world, we very rarely, I hope, ever get to a point where things are saturated solution, because most chemicals are present at very low concentrations in the grand scheme of things. But this is true at saturation, that you could get the Henry's law constant by just dividing the vapor pressure by the solubility. And I think it's a useful concept. It's a nice way to sort of think about the problem. But they eliminated this from the second edition of the textbook because it's not pure enough, and they're very, they're Swiss, and they like things to be accurate and correct all the time. But I like this concept, so I introduced it here. So anyway, again, you can think of Henry's law constant as being the vapor pressure divided by the solubility. So one of the, when you do that thought experiment, you say, okay, let's say we have a compound that's quite polar. It's hydrogen bonding. That means that its solubility is high, but its vapor pressure is low, and therefore its Henry's law constant is going to be like extra, extra low, like low, low, low. Okay, so that makes sense. But what do you do if a compound has both a low vapor pressure and a low solubility? Oh, what is its Henry's law constant going to be? But that's a useful thought experiment to do. And that's why we just saw this slide where we said, look, vapor pressure ranges over 12 orders of magnitude. Solubility ranges 12 orders of magnitude. But Henry's law is only 7 or 8 orders of magnitude. Because you're dividing one by the other, you're sort of factoring out a lot of the variability. So Henry's law is a balance. And there's plenty of chemicals that don't like the water, but they don't like the air either. So they're kind of stuck between the rock and the hard place. All right, what factors affect Henry's law constant? This is going to come as zero surprise to any of us. Temperature, of course, salinity, yes, and co-solvents. So we've already talked about salinity and co-solvents and temperatures, so that's why this lecture goes fairly rapidly. So just like all of our equilibrium constants, we can adjust our Henry's law constant for temperature by using an equation of this form, where we have our delta H term for moving the chemical between the air and the water. Here it's AL, but if we're talking about water, this would be AW. And that's all fine. Again, you can use it to convert from one temperature to another. This is all fine. Everything is well and good until we get to the point where we're using dimensionless units. Because to convert from dimensioned to dimensionless units, we have to divide by RT. So if this has units, if this has pressure units, then to get it into dimensionless units, we have to, sorry, I know my slide was getting a little bit busy, but here if we have pressure units of something like Pascal meter cube per mole, we divide by RT to get dimensionless units over here. So we've already divided by RT. There's already an RT in here. And when we do our temperature correction, we got some R's and some T's flying around. And if we just left this as dimensionless Henry's law and we did our conversion here, we'd be going astray. So to fix that, we have our little RT average here. You have to use this extra special form of the equation. If you're going to use dimensionless units, you have to use this special form of the equation that has RT average in it. Okay, well, what is the value of this delta H term? Well, so to move the compound from air to the liquid, which, again, is mostly going to be water, we have to first vaporize it and then dissolve it in water. So if we're talking about the pure liquid, first we have to vaporize it. So here's your delta H of vaporization, right? And first we have to vaporize it, okay? And then we condense it back down into water. And so the Henry's law constant, the delta H of Henry's law, is the difference between these two. It's this value right here, delta H Henry. I know I'm going a little crazy with the telestrator today. You got to forgive me. It's been a long day. All right, so what that means is that the Henry's law constant is going to be slightly less than the delta H of vaporization if He is positive. But remember from the solubilization lecture, the whole lecture on aqueous solubility, we said, first of all, this is pretty small. I mean, it's not a huge number to begin with, especially if you're talking about small molecules that don't have a big cavity term, and they make a lot of sense. There's not a lot of issues there. So the He is pretty small, and therefore delta H of vaporization and delta H of Henry are often quite similar to each other. So again, it's very easy to get confused about what delta H terms we're talking about. So I made this handy little graphic. Ooh, lunch. And I tried to show this in a way that actually gives you some sense of the scale of things, so that the gas phase is way up here at the top, right? Because that's a high amount of energy. Remember, I keep talking about how it's like launching the space shuttle to try to get this stuff into the gas phase. Moving anything into the gas phase takes a lot of energy. It's launching a rocket. So the gas is way up here. The amount of energy to get there is pretty high. So if you're in the pure liquid, the amount of energy required to dissolve in water is here. That's the HEW term, which mysteriously lost its delta. God knows, still can't figure out where it went. And to get the pure liquid into the gas phase is here, delta H of vaporization. And so the partitioning from the gas to the water here, for Henry's law, is the balance of those two things, right? And of course, if we have a solid, we'd have to melt the solid to get it into the gas phase, and we would still have to melt the solid to get it into the liquid phase, to the water phase. So it turns out that it doesn't matter whether our compound is a gas or a solid. The Henry's law constant is always going to be right here. The delta H for Henry is always going to be right here. And what that means is that the phase change costs cancel out. It doesn't matter whether your compound is now a solid or a liquid. So if you spent the first 2 weeks of class thoroughly confused about that whole concept of the hypothetical subcooled liquid, you can relax because you can forget all about that now. Okay, and remember, delta H of vaporization is always pretty big, right? That's why I draw the gas way up here, because it takes a lot of energy to get up here to the gas phase. Whereas this He term here is usually on the small side. And so if we look at a comparison of delta H of vaporization for delta H of Henry's law for a bunch of different chemicals here, we often see that there's not much difference. I mean, sometimes there's no difference. Sometimes there's a difference. But a lot of times there's really not much difference. The differences are quite small. Especially when you have small molecules, which are kind of in this range. We're kind of increasing in molecular weight as we go down here. And also these are neutral chemicals over here, for which it doesn't make much difference. So what that means is that if you can figure out what delta H of vaporization is, then you can basically just substitute it for a delta HAW as long as you're dealing with a small molecule that's not strongly hydrogen bonding. So when you do have a difference between the two, you generally see that delta H of vaporization is bigger than delta H for Henry's law. Sorry, I tried. I do the best I can with my mouse. Here. There we go. Okay, so you see that the delta H of vaporization is generally bigger than the delta HAW for these neutral chemicals, and that the difference gets bigger and bigger as you go up in higher molecular weights, right? So when you get to big molecules, like here's hexachlorobenzene, here you got some PCBs over here, this is lindane, gamma HCH, then the differences start to be significant. and you may need to estimate the HEW, that excess enthalpy of dissolution, and subtract it off of delta H of vaporization. But then the other thing you notice is here, when you start to get to really strongly hydrogen bonding chemicals, now delta H of vaporization is smaller than the delta H of Henry. And that's because dissolving these chemicals in water is very favorable because they can hydrogen bond with the water. So you actually get a little bit of energy back. And so here you'd have to figure out that excess enthalpy of dissolution, and it would be negative. So you'd be subtracting a negative off of the delta H of vaporization, and you'd end up with a higher delta HAW than you have for delta H of vape. But the take-home message is when you get stuck, if you can't find HE, then just use delta H of vaporization and hope for the best. Now the other take-home message here, though, is here we have these strongly hydrogen bonding chemicals, and we might be really worried about how we could accurately predict HAW for these chemicals, delta HAW. Well, guess what? It doesn't matter because these guys are strongly hydrogen bonding, therefore they have very, very low Henry's law constants to begin with. And not very much of them is going to end up in the gas phase anyway. So wasting your time on determining whether it's 1% or 2% of the total, it doesn't matter. The delta HAW doesn't matter so much because they just don't volatilize much. Effective salinity, we already saw that you can use the Seshnow constant to predict changes in the solubility based on salinity. Well, it turns out you can do the same thing for the Henry's law constant. The Henry's law constant in the presence of salt is equal to the Henry's law constant with no salt times the same correction factor 10 to the function of Ks times the molar salt concentration. And the reason we can get away with doing this is by making the logical, rational assumption that the salinity will increase the Henry's law constant by decreasing the solubility side of the equation, but will have absolutely no effect on what's going on in terms of the vapor pressure, right? So if we think of Henry's law constant as vapor pressure over solubility, the Seshnow constant, the salting constant, is affecting the solubility side of the equation, but not the gas side at all. And by the same logic, we can use those equations that we developed for cosolvents here to predict how Henry's law will change depending on the volume fraction of a cosolvent. So now we're going to talk a little bit about, that's it, really. That's all I have to say about Henry's law constant. So I'm going to talk a little bit about partitioning and how you would calculate how compounds partition between two phases, because here we have water and air. Let's think for a moment about how a chemical will partition between an air and water phase. So let's say we have like a little serum bottle. I'm going to do my best with my crappy Lamass pointer here. Okay, so here's my little serum bottle. Okay. And I've got some water and I've got some air, and my chemical is partitioning back and forth between these two phases, right? And the serum bottle might come to equilibrium. So the total mass of my chemical is the sum of the mass in the air plus the mass in the water. That will give you my total. The mass in the air can be written as the volume of the air times the concentration in the air. Same thing for water. The mass in the water is the volume of the water times the concentration of your chemical in the water. So if I want to calculate my total, my fraction of the chemical that ends up in the water phase, for example, that would be the mass in the water phase divided by the total mass, which we could also write as MW divided by MA plus MW. And then we substitute in the volumes here, we get this, right? And then something magic happens. How do we get from here to there? Okay, I don't know why my pointer just does not want to work properly today. Anyway, how do we get from here to here? Where did the Henry's law constant come from? What the hell just happened? Okay, the way to do this is divide each term by CW. If you divide this term by CW, CW cancels out. Divide this term by CW, CW cancels out. Divide this term by CW, you get CA over CW. Voila, that is Henry's law. And really, this should be KAW because we're doing concentrations. And so this would have to be our dimensionless Henry's law constant here. Okay, so now notice, the fraction of the chemical that ends up in the aqueous phase is a function of the volume of the aqueous phase, the volume of water, the volume of the air, and the Henry's law constant. That's it. Nothing else. Nothing else matters. Temperature matters, salinity matters because they affect Henry's law, but nothing else matters. Okay, Last little topic here. I'm just going to talk very briefly about how you measure Henry's law constant. There's two main approaches, static and dynamic, but the real point of this part of the lecture is just that measuring Henry's law is quite difficult. Of all the equilibrium constants that we've talked about, vapor pressure is on the easy side, solubility is difficult, and Henry's law constant is really difficult. It's a pain in the ass. And for this reason, there really aren't as many measurements of Henry's law available as there are for other things. So very frequently when you look up a Henry's law constant, what you're going to find is not a measured value, but rather a estimated value based on bond contribution methods and stuff. And there's a whole separate lecture on estimation techniques and using them to predict things that I'll have you watch a little bit later. And it's particularly hard to measure when the solubility of the compound is quite low. So there's two approaches. There's the static and the dynamic. The static is where you typically, I did this when I was in grad school, you take a syringe, it has a stopcock on it, to close it off, and you put some of your compound in the aqueous phase in the syringe, you expel all the air, and then you suck in, like say you have 50 milliliters of water, you suck in 50 milliliters of air, so you got a 50-50 situation, and then you sit there and you shake it, and you shake it, and you shake it, and then you shake it some more. And then when you're done with that, you shake it for a while to make sure that things come to equilibrium. And then once they've come to equilibrium and you're confident that they've come to equilibrium, you measure the concentration of the chemical in the gas phase. And then you expel the gas phase from the syringe, suck in a new clean 50 milliliters of air, close the stopcock, and then you shake and you shake and you shake some more. It's very, very annoying. And you wear a glove on your hand so that the heat from your hand doesn't warm up the syringe. It's awesome stuff. Yeah, I got to do this. Terrific. Anyway, so as we've just seen, the fraction of the chemical that's in the water is a function of the Henry's law constant and the volumes of the air and the water. And you know the volume of the air and the water. And you know how much you're expelling every time you expel the air. So you know how much is disappearing each time, which lets you calculate how much is left behind in the water. You know VA/VW. From that, you can back out the Henry's law constant. The trick here is that you need a large enough fraction of your chemical to go into the gas phase and get expelled each time so that you have a measurable change in the concentration in the air and therefore in the concentration in the water. It's just easy to measure the air. You need a measurable change. You need some significant fraction of your chemical to go into the gas phase and then get expelled from the system. And if your Henry's law constant's really low, then that's very difficult to do. You can adjust, again, we've seen the fraction that gets in the water and by definition also the fraction that gets in the air is a function of the volumes of air and water and the Henry's law constant. Well, you can't change the Henry's law constant. That's what you're trying to measure, but it is what it is. You can't change it. So all you can do is adjust the amount of air and the amount of water. Now you're having a hard time getting enough of your chemical into the air to be able to see it disappear. So you want to increase the amount of air. But there's a practical limit, what, 10 milliliters of water and 90 milliliters of air maybe is the practical limit of this syringe technique. So what you really need is a system where you can have a lot more air compared to the amount of water you have. And that's where you get this dynamic system where you have your chemical in the water and you spike it into the water and then you bubble air through it and the air strips the chemical out. And then you can apply some equations, you can back calculate how much of your chemical is disappearing over time, and you know the flow rate of the gas, and you can back out the Henry's law constant. Now this has problems too because there turns out there's some weird partitioning stuff that goes on the surface of bubbles. The surface of the bubble is not the same thing as the water and not the same thing as the air. It's got its own special properties. So this gas stripping technique isn't perfect either. But those are the two main methods that people use to determine Henry's law constant. So that's all I have to say about Henry's law constant. Where it gets interesting is when we start to do some example problems. So look for those, and they will help you make a lot more sense of the whole thing.